Welcome to this week's Short Clip Friday podcast. On Fridays, I will be posting clips from previous episodes, and the point here is just to bring you some of the highest yield topics from each podcast in order to kind of reinforce those topics. This clip is from my upcoming audio course, which I hope will be out by the summer. It covers how to calculate oxidation states. Enjoy. Calculating oxidation state. Oxidation states are indicated with positive and negative integers, +1, -1, +4, +8, -3. The oxidation state of a molecule is how many electrons an atom would have if all of its bonds were completely ionic. And if you're like me, that might make you say, huh? What does that mean? Well, take sodium chloride for example, NaCl. Sodium chloride is a fairly familiar ionic compound. And we all know that when sodium chloride dissolves, it dissolves into ions. And the sodium ion has a +1 charge, and the chloride ion has a -1 charge. And further, we know that these charges exist because sodium donates an electron to chlorine to complete both of their octets. So that means that in this context, sodium has a +1 oxidation state, and chloride has a -1 oxidation state. This is a pretty obvious example, but I want to get into more complicated molecules that aren't ions like CH4 or methane. But before we address those more complicated molecules, let's lay down a couple ground rules for assigning these oxidation state numbers to different atoms and to different molecules. And there are 6 ground rules that I want to talk about. 1. Atoms in their elemental state have an oxidation state of 0.
Elementary, my dear Watson.
For example, this would be like gaseous hydrogen and oxygen, H2 and O2 respectively. 2. When hydrogen is combined with a nonmetal, it has an oxidation state of +1. Examples of this include methane, CH4, and sulfuric acid, H2SO4. So again, in both of these compounds, hydrogen has an oxidation state of +1. 3. Hydrogen combined with a metal has an oxidation state of -1. So in a lithium hydride and sodium hydride, LiH and NaH, hydrogen has an oxidation state of -1. 4. Monoatomic atoms, which are just atoms by themselves, have an oxidation number equal to their charge. So for instance, oxygen alone has a -2 charge, sodium alone has a +1 charge, and therefore monatomic oxygen has a -2 oxidation state, and sodium has a +1 oxidation state. 5. Here's to me probably the biggest rule, and that's that the oxidation state for oxygen in any molecule is usually -2. And similarly, you can think about halogens and the group 1 and 2 metals as having the same oxidation state as the charge that they would have as an ion. So for instance, sodium likes to have an oxidation state of +1. Fluorine likes to have an oxidation state of -1. Lithium likes to have an oxidation state of +2, and so on. So let me just reiterate real quickly, because again, I think this is probably the most important rule of them all. The oxidation state for oxygen, the halogens, and the group 1 and 2 metals is the same as the charge that they would have as an ion. 6. For a molecule, the oxidation states of each element in the molecule should add up to the overall charge of the molecule. So for example, take potassium permanganate, KMnO4. The oxidation states of the 3 elements that make up this molecule, potassium, manganese, and oxygen, need to add up to the overall charge of potassium permanganate, which is 0. Take an even harder molecule, the complex ion hexaqua iron 2. This is essentially 6 water molecules attached to a single iron, which overall has a +2 charge. So that means that the oxidation state of the iron, hydrogen, and oxygens in this molecule must add up to be +2. Now, there are a few places that you might see this come up on the MCAT, and in all of which you'll need to determine the oxidation state of an atom in a molecule. So let me kind of just tie together these rules with an example. Find the oxidation state of manganese in potassium permanganate, KMnO4. So the first thing I do here is find the oxidation states of the elements in which I know their oxidation state. So that's going to be potassium and oxygen, right? Because we know from one of these rules that the oxidation states of these molecules must be equal to the charge that they would have as an ion. So potassium has an oxidation state of +1, and oxygen has an oxidation state of -2. And by the way, that is the oxidation state for each oxygen. And since there's 4 oxygen atoms here, the overall oxidation state of O4 is -8. Now, as we know, the overall charge of the molecule is 0. So the oxidation states of each of these individual elements must add up to 0. And so far we have that potassium has a +1 oxidation state and O4 has a -8 oxidation state. So you can then ask yourself, what does the oxidation state of manganese need to be in order for the sum of these oxidation states to equal 0? It's just going to be +7. That's pretty easy math. 1 minus 8 plus 7 is equal to 0. So the oxidation state of manganese in potassium permanganate is +7. And I should mention too that a lot of the transition state metals can have different oxidation states depending upon the molecule that they're in. So there's no quick and fast rule for, iron is always +1 or is always +2. It can be a range of different values depending upon the molecule it's in, which is why you first kind of work through the different elements in a molecule that you know and you can nail down their oxidation state, and then you use the other rules to essentially back calculate the oxidation state of whatever molecule you're interested in, like manganese in our example. That's a pretty good example of something that you might see come up on the MCAT, as well as a good summary on calculating oxidation states. So I'm going to leave it there. MCAT Audio by Med School Coach. Hey everyone, I'm going to be on Twitter Spaces on Wednesday, May 26th at 3 p.m. Eastern Time. I'm basically going to do a MCAT Basics question and answer. So bring your questions about the MCAT, about med school, really about anything, and I'll try to answer them. I'm going to be doing the Twitter Spaces on the Med School Coach Twitter account. The handle for that account is @MedSchoolCoach. I have included that in the show notes for this clip episode.